Hey everyone, today we're going to talk about fake process groups and fake tensors. So to motivate this, why do we need these? These are primarily useful for two use cases. One is when you don't want to do the actual computation. So for example, if you're trying to do a flop counter, and you're trying to count the number of floating point operations in your model, you might want to use these fake tensors or process groups to kind of simulate computation without actually doing it. And the second big one, the one that I'm more interested in these days, is this idea of cross-compilation, where you can actually compile a program for GPUs on a box that doesn't have a GPU. And so this is quite useful in the large-scale training these days, where you might want to compile a CUDA program on a non-GPU box, and then when you're actually doing training, you can just move this artifact to each of the GPUs and just run it. And so you don't have to do any just-in-time compilation. It's all ahead of time. Okay, so how do we use these abstractions to accomplish that? So the first one is called a fake process group. And as a refresher, a real process group is kind of like a group chat between your GPUs. So typically, you'll have these process groups that are subsets of your overall topology, and when you run a collective with a process group, these different ranks will talk to each other. So they might average a tensor, they might concat a tensor, etc. What a fake process group does is it's fake. So you can run these collectives with these fake process groups, and instead of doing communication, it will just kind of return to you the tensor of the sizes and strides that you would have gotten if you had done a collective. But of course, the actual numerics of that tensor means nothing. But this is still very useful, for example, if you're doing compilation and you need to make sure that the sizes and strides flow through your graph. What's a fake tensor? So again, on the left side, we have what happens without fake tensors. So if you do torch.randn 5 device equals CUDA, what will happen is we will allocate a tensor of size 5 on the GPU. And when we call torch.cat AA, we will invoke a GPU kernel which will concat A to itself and create a new tensor. What happens with fake tensors? So the way that you use fake tensors is by activating fake tensor mode. And if we do this torch.randn 5 device equals CUDA now, what we will get instead is a fake tensor, which is a subclass of tensor. And a fake tensor has a attribute called fake device. And the fake device of this fake tensor will be CUDA. But the actual tensor that this fake tensor is will actually be on type device meta. And so what this means is, as we're compiling your model, or cross-compiling your model, we're able to run these meta kernels and get the correct sizes and strides. So for example, if we call torch.cat here, it will actually invoke a meta kernel, which is effectively just a function within the PyTorch codebase that says, for cat, given these two inputs, what is the expected sizes and strides of the tensor outputs? And so with this, we can do cross-compilation with these fake CUDA tensors. So lastly, let's take a look at the code. So how do we do this in practice? The way we do this in practice is we first initialize the model on a meta device. And the reason we do this is because when we apply things like parallelization, it does not compose well with fake tensors. And so typically what you'll do is you allocate your model on a meta device, you parallelize your module, and then you enter the fake mode. In the fake mode, once you're in the fake mode, the first thing you do is you convert your model to your target device. In this case, you would convert the model to CUDA. And under the hood, what's happening is each parameter and buffer is actually being converted into a fake tensor with fake device CUDA, and then the real underlying device is meta. And then here you also create fake tensors for the inputs to your model. In this case, it will be a D tensor. And then you run your compilation pipeline with this fake model and these fake inputs. And after all of this, what you'll get out is a file. And what's really cool is, although the tensors and the model that you use for compilation were quote unquote fake, this artifact that you write out is very much real. And so you can just load this artifact on your current machine, on a different machine, with the target device, and you can run it with real tensors. So here you can see that we read from the file, and we basically deserialize it into a callable. And then here we create some real tensors on real devices. We initialize the model, and then we're actually able to run this cross-compiled function with real inputs and actually get real outputs. So yeah, hopefully this was helpful in kind of building more intuition on what these fake process groups and fake tensors are. And I will see you in the next one.